Okay, so far we've been talking about second order linear ODEs and shown you cases where you can solve these linear ODEs in closed form. And those are only the ones that have constant coefficients with P naught and Q naught and whatnot. And for the, if you remember, we had this guy, okay, and this had the corresponding problem, the non-homogeneous problem, so to speak, and okay, and then we saw that this is so obviously solvable in closed form, even when you have repeated roots for that characteristic equation when you put y equals e to the power RT, and then you can get another linearly independent solution by this method of reduction of order. We discussed that to get two linearly independent solutions, and then I also spoke a little bit about the Wronskian and the fact that you can use that as a measure to see if two solutions are linearly independent and so on. Okay, so this is done. Yeah, we spoke about this, and then we came to this. We said, okay, you can use, when you have some arbitrary f, you can just use the same variation of parameters to get a particular solution, u1 of t, y1 of t plus u2 by 2, and then you put this in two functions of t, unknown functions. You can put the auxiliary equation, you will get expressions that look like integral of f y2 divided by Wronskian and stuff like that. Okay, so we've been able to solve this as well. So this problem is done, and then we moved on. I told you again our underlying hierarchy that we always keep in mind, the fact that the exact solution is the best, and then the next best thing is quadrature, and then the next one is the approximate analysis or semi-quantitative stuff. That's what we started doing, and that's where I'll start off today. And today's discussion will be a little bit heavy. I don't expect many of you to have seen any of this stuff before, because this is usually not taught in an undergraduate course. It's a little bit advanced, but given what we've already discussed with respect to first order equations, and that's the reason we spent time on first order equations, given that background, you should be able to follow this and in principle work this out by yourself. Okay, so if you know the basic ideas, you should be able to work it out by yourself, and I highly encourage you to do that. So I would recommend that you actually try it out and go sit down with lots of paper and a good cup of tea or something and try to figure this out. Okay, and you can do it, I'm sure. So the beginning point for this, of course, was this phase space, and if you remember, we said, okay, you have a second order equation like this. We assumed some arbitrary p of t, some arbitrary q of t. Okay, and we said you can reduce this to two coupled first order equations. Okay, and then we said you have two situations, you have y naught and y1, and then you have a dy naught by dt is y1, and then you have dy 1 by dt is whatever, right? Could have p, q, whatever, right, on the right hand side. Now we'll of course, the reason we're doing this stuff, the semi-quantitative analysis, is because we've not really said anything about nonlinear second order ODEs. Okay, nonlinear second order ODEs are more common than you think, and I'll give you several examples. We'll even have a tutorial session on this next, where you'll see some examples and we'll work out all of this theory in that context. But we've really said nothing about nonlinear second order ODEs, right? We've only been talking about linear second order ODEs, and we've had a lot of trouble just with that. We haven't been able to solve even the general linear first order ODE, linear second order ODE, pardon me. And so we sort of got stuck there. We still haven't progressed, graduated to the nonlinear case. And so in view of doing that, and again, that's where, just like for the 1D case, this semi-quantitative stuff was most useful when you had some arbitrary f on the right hand side. So if you recall for the 1D case, you had dy by dt equals f of y. Okay, and so that means that you have some arbitrary function. This is some arbitrary nonlinear function. Could be anything of y, and notice this is autonomous, so we don't have any t dependence explicitly here. We don't have a separate term that has a t dependence like the f of t that we have here. So this is autonomous, it's an autonomous system. So our view now will be to take what we learnt here and try and apply it to the general nonlinear second two-dimensional or equivalently second order case. So now what we want to do is we want to do dy naught by dt is some f of y naught y1 and dy1 by dt equals some g of y naught y1. Okay, now this is the generalized, the more general version of this, the nonlinear version, second order nonlinear version of this. Okay, so two dimensional. That's the prototypical system we are going to be concerned with. And all the stuff that we have here without a function of t, of course, now again we are assuming it's autonomous, there is no explicit t here, notice that. I will tell you what we will do for the non-autonomous case in a minute, but let us set this problem up before we get there. And so you have pq, if you have pq constant, then that is non-autonomous, and that will be a special case of this. Yeah, so if you had p naught and q naught instead of p and t, you had p naught and q naught. If you had this, then dy0 by dt is y1, dy1 by dt is minus p0 y1 minus q0 y0, right. So this is a special case of this, where the arbitrary nonlinear functions f and g are linear functions. So there you can have f of y0 comma y1 is basically just y1, and g of y0 comma y1 is just p0 y1 minus q0 y0. Okay, so it's just a special case of that. So we'll look at this general case. That's what we want to do. Okay, that's where we want to go with this stuff. We want to go to the general case. Now, in order to be able to do that, we need to know what to do with this. Okay, this is the general case. Remember, again, purely by analogy, 1D, 2D, this was 1D, and like I said, that's the reason we spent some time on the 1D case. We were looking at this stuff, and this is the 2D analog of this. The idea that we want to now execute is we want to see what we did here and try to do the analogy here. Okay, so what is the first thing we did over here? You remember we first find the fixed points, and what were fixed points here? The fixed points were just dy by dt equal to 0. So f of y star was 0. So if you started exactly at the fixed point, you would stay there forever. That was the definition, right? So for this case, we had f of y star equals 0. Now we do the same thing, but now you have to set both derivatives equal to 0. So if you are not going to move from a certain point, so this is phase space y0, y1, and if this is the fixed point y star, now it has two coordinates y0 star, y1 star. One is the horizontal coordinate, one is the vertical coordinate. And if you are going to, if this is going to be a fixed point, then you are not going, if you start exactly here, you are going to stay there. That's how we defined a fixed point, right? So that means both the derivatives have to be equal to 0. So now the analog of this step will be doing f of y0, y1 star equals 0, g of y0 star, y1 star equals 0. So you have two nonlinear equations to solve for two unknowns, and you can in principle solve them. Okay, so that is the first step. So first step, okay, directly follows through. What was the second step? The second step was linearization. So we did then linearization about y star. Okay, and what did we do here? We said for the 1D case, we said eta of t is y of t minus y star. So very close to the fixed point, we linearize the equation. And how do we do that? We take the right hand side f of y is f of eta plus y star, and then we opened it in the Taylor series. We got df by dy at y star times eta plus some additional terms which we dropped, and so you basically had d eta by dt, which is the same as dy by dt, is equal to f of y, and so you have d eta by dt is df by dy times whatever, right. This is the standard linearization that we did for the 1D case to talk about the stability of these fixed points, right. Are these fixed points stable, are they unstable, are they saddles, whatever. Okay. So now we have to find a way to do that here. So that is slightly non-trivial, certainly more non-trivial than this. So we have to linearize about a fixed point, and now notice fixed point has two coordinates. So you have y0 star and you have y1 star, two coordinates. So you have to linearize about, you have two equations, and you have two coordinates, and so you have to, presumably linearization will now have two equations. Okay, we'll see what that is. And then the third step, which becomes even more non-trivial, is finding the stability. Okay, in this case it was easy because you only had one fellow and you had a linear system, and you can solve a linear system, and first order linear system is probably the most trivial ODE you will solve. And so we only had to look at this df by dy, is it greater than 0, less than 0, whatever, it's stable or unstable depending on that, right. So we said linearization, you can do that. Okay, good. So then what happens? The analog now becomes a little bit more complicated, okay, because you've linearized, and we'll see how to do that. I'm not telling you how to linearize right now, we'll come to that eventually. You're linearizing a nonlinear equation about the fixed point, just like in the 1D case. Now in the 2D case, now you have two, so you have two linear equations about a fixed point, and so you have to now determine the analog of this for the 2D case. Okay. Now why is that complicated? It's complicated, well, it's actually not complicated, but certainly it's complicated compared to this, because here you have only one function. Remember, ODE only had only one f, and you had only one variable, so you had only one derivative. Okay. Now you have two functions, f and g, and you have two variables, so you presumably have four derivatives: dou f by dou y naught, dou f by dou y1, dou g by dou y naught, dou g by dou y1. Okay. So you have four derivatives now. So what combination, which of these should be positive, which should be negative, which can any be 0? Those are all things that will now come up. Okay. So this is slightly non-trivial, and it turns out that you can, once you do linearization, you can derive conditions under which a fixed point will behave like a stable node or unstable node. Two possibilities, of course, that's the same thing that we had for the 1D case, or a saddle. So those three possibilities we've already seen for the 1D case, but in addition, now additional, there are further possibilities that come up. Okay, the fixed point can become a center, what's called a center. So you can have trajectories going around the fixed point. Okay, you can have fixed points that become spirals. So trajectory starts, it rotates around the fixed point, eventually reaches the fixed point. It's a stable spiral, right? So you can start having these new types of behavior that you never really had here, simply because you have more things of this kind in the second order system, in the 2D system that we're talking about. Okay, so that's a brief sort of sojourn into telling you why this stuff is non-trivial and certainly more interesting than the 1D case, and sort of justifying why we spent time looking at the 1D case, because we can get here. And the procedure is again analogous, but the algebra is a little bit more tedious. Well, not too much, but okay, slightly more tedious, certainly not non-trivial compared to this. Okay, so we'll do that in two steps. First step, we'll simply look at linear systems, and by linear systems we mean something that looks like this: dy0 by dt. I'll just use y1 and y2, okay, from now on, just so that it makes things easier. So this is ay1 plus by2, cy1 plus dy2. Okay, and the general second order system that we had is just a special case of this. If you put a equals 0, you will get dy1 by dt, and b equals 1, and then you put c equals p naught and d equals q naught, you will get the same second order constant coefficient ODE that we started with. Okay, so this is the more general version of it. Okay, Good. So now what can we say about this system? Let's do the same stuff that we did for this system, okay, that we just outlined here for understanding their behavior. Now again, remember we're looking at semi-quantitative stuff, so we're looking at things potentially like the question what will happen as t goes to infinity, what will happen to the trajectory, okay, that's a question that you can ask. That's a type of question you can answer with this type of analysis, okay. Now presumably this is solvable. I've been yammering about this being solvable, the only 2D system that's solvable, but we'll start with this because it's illustrative. And then when you go to the nonlinear case, you're anyway going to linearize, so you're going to end up with something like this. And whatever we learn from here, we can just directly take and apply for the nonlinear case. Okay, so that's our strategy. So let's start this procedure. What is the first one? What are the fixed points? Okay, the fixed points are obviously where the left hand side is 0, the derivatives are 0. So you have a y1 star plus b y2 star equals 0, and then c y1 star plus d y2 star equals 0. Okay, and for any arbitrary a, b, c, d, remember a, b, c, d are arbitrary constants for now. For any arbitrary set of constants, these two equations will only give you one solution, which is that y1 star equals 0, y2 star equals 0. Okay, so a linear system of this form, linear 2D, we'll call this a 2D system because it's got two coupled linear first order differential equations, and it's also 2D because the phase space is two dimensional, so we'll call it 2D. So a linear 2D system has only one fixed point, which is at the origin. Now compare this again just for completeness with the linear 1D system that we had. This was just k times y, and the fixed point for this also was at y star equals 0, okay, which is again the origin. So linear systems always have fixed points at the origin, right? You can clearly see that from here. Okay, so that is good. So fixed point is at the origin. So get rid of this. Fixed point is at the origin. Okay, so this is the fixed point for this system. So this I'm going to call 1. Okay, good. So now the second point, what can we say about the stability of this system? What about linear? Okay, linearization is trivial. We already started with the linear equation, so there's nothing really to do here. But what can we say about the stability? Okay, now this question is a little bit more complicated, like I said, about for a second order system, for a 2D system, and it has to do with the fact that I think I've specified this multiple times before. If I start here at some arbitrary initial point, so let me, this is y1, y0, y2, let me start at an initial point. This has alpha and this has beta, so I'm starting at the initial location alpha comma beta. Okay, that's where I'm starting, and I want to know now if I start at some alpha comma beta, presumably close to the origin, since that's the only fixed point, what will happen to a trajectory with this as initial conditions. Notice alpha beta are initial conditions, so y1 of t equals 0 is alpha and y2 at t equals 0 is beta. So given these initial conditions, if I start from here, and if I had solved this system, which I know I can, but okay, you know, whatever, if I had solved this system, where will the trajectory go as t goes to infinity? That's the first question I can ask, right? Will it go close to the origin, which means as t goes to infinity, so if as t goes to infinity, y of t approaches the origin, y of t divided by, okay, y1 of t, y2 of this trajectory, right? Trajectory is now a curve in this plane. Will this approach the origin? Okay, that's one possibility. If it does, then this is precisely what absolute stability was. We defined absolute stability and we spoke about this earlier. Okay. The second possibility is, okay, maybe then it will go away, far away from the origin, in which case it's absolutely unstable. But now, unlike the 1D case, there is a third possibility. A third possibility is that if I start here, I'm basically going to be circling the origin. Okay. So why are these two cases different? Why? Okay, the first two, stable, unstable, is clear. But why is the third case important? Third case is important for the following reason. Remember, we defined this thing called Lyapunov stability. There was even a question in one of the interactive sessions about this thing, and the Lyapunov stability asks the following question: if we have y0 minus for the 1D, so look at what it was for the 1D. If we had y0 minus y star is less than delta, then is y of t minus y star less than epsilon, both being very small numbers for all t. So we had asked this for the 1D case. Remember, this was what we had said. Okay. Now for the 2D case, we can generalize this idea and say if I have a vector y bar 0, that is the initial condition. Okay, this is my y bar 0. Maybe I'll use a different name. Maybe I'll call this r0 bar. Okay, that's the vector. If r0 bar minus the origin, the fixed point, okay, this is y star bar. Y star bar. Now y star bar is the origin, but I'll still put it there for generality. If the magnitude of this vector, this has two components, notice this is alpha beta and this is y0 star y1 star. In the linear case, again, this is the origin, it's trivial, but I'm going to keep it for generality. If the magnitude of this vector, the difference between these two, the magnitude of this vector is less than delta, so you start a certain distance from the origin or from the fixed point, and then you ask the question, is the magnitude of y bar of t minus y star bar of t, y star bar, sorry, is this less than epsilon? So it's a simple generalization of this. So instead of just taking two numbers, I'm taking a vector and calculating its norm or the length. Okay, and if I do that, again, y of t is y1 of t comma y2 of t, two coordinates, and this is just y star, whatever. Okay, if I do this, or if this is true for all t, then this y star bar is Lyapunov stable. Okay, the analog of this, the analog of the absolute stability, is simple enough to state. If you have the same initial thing like this, but then t goes to infinity, if the y bar of t approaches y star of t, which means both coordinates approach the fixed point, then it's absolutely stable. We've discussed that. Okay, so this Lyapunov stability now becomes distinct from the absolute stability case. Whenever something is absolutely stable, that means it's Lyapunov stable, trivially, right? Because if something is absolutely stable, t goes to infinity, it's going to come here, and that means this is automatically satisfied. However, the converse is not true now. Okay, and this is an example that illustrates this. So if you have a closed orbit around the fixed point, like in this case, then the converse, which says something is Lyapunov stable but not absolutely stable, is true, right? You can have something that's Lyapunov stable, like this trajectory, because this is, if you start presumably close enough here, this length is delta, then I'm always going to be in the vicinity of some small epsilon that is comparable to delta, and it's going to be around this point. That's possible in 2D, just geometrically speaking, that's possible. You can go around and around. So there are situations where Lyapunov stability now is different from absolute stability. Okay, so that is something you want to keep in mind. Good. So let's get back to this system. Okay. Oh, incidentally, one more comment I'd like to make before I continue is that if you look at this one, right? This one system is actually is more general than it first appears. Of course, the 2D system can be reduced to this. Like I said, if you put a equals 0, b equals 1, whatnot, it can come reduced to this. But you can also take a non-autonomous 1D case and reduce it to this. Okay, I'll show you how in a second. Let's say I have a system that looks like this. This is a non-autonomous, non-linear. This f is general, non-linear, because f depends non-linearly on y, not because it depends on t. Right? We've already stressed that part several times. But it's also non-autonomous because it depends explicitly on t. Autonomous Okay, and so now if you have a situation like this, clearly the stuff we did for the 1D case is no longer applicable because you have this t here. So it's not just f of y and do whatever stuff that we did last time won't work. But there's a little trick you can do, which is you define now y0 is equal to y, and you define y1 is equal to t. So you can convert this non-autonomous 1D system to a 2D system. Okay, and how do you do that? Well, this is simple enough. So you have dy by dt is dy0 by dt, and that is f of y, which is y0, and t, which is y1, and dy1 by dt is just dt by dt, that is equal to 1. So now we have a 2D system. Okay, so in principle you can take any non-autonomous 1D system, make this dummy variable change and make it a 2D system. It's sometimes called a 1.5D system in certain situations, but this is the idea. Okay, so now whatever we say for 2D systems, you can just take and apply to a non-autonomous non-linear 1D system. If I had a non-autonomous non-linear 2D system, I can do the exact same trick and make it a 3D system. Okay, I will just add another one. So I have y1, y2, I'll change y3 is equal to t, and then I'll get dy3 by dt is equal to 1, same thing. Okay, and I can go higher up. So I can keep doing this. Anytime I come up with a non-autonomous system, I can just bump up the dimension by 1. That's an easy enough trick to do. So really non-autonomous systems are not that difficult to solve. I mean, they're difficult because they increase the dimensionality, but we know how to handle them. Okay, just a side note. Good. Okay, so the next step is the following. Okay, now we want to look at the stability of the system. So the origin is only fixed point, we figured that out, and we want to now ask the question, what is the analog of df by dy y star thing that we had before? What is the analog of that in this situation? Okay, now I'll do that. I can give you the general theory, of course. I can work it out and keep ranting all along because I'm here by myself, but instead of doing that, I'll give you 2 examples. Okay, and then we'll build it up slowly from there so that things become somewhat clear. So let me do the first example. So example 1. Let's say I have dy1 by dt is alpha y1 and dy2 by dt is minus y2. Okay, that's the same thing. It's the same as the linear system we wrote down. Let me write down the linear system here. dy1 by dt is ay1 plus by2. dy2 by dt is cy1 plus dy2. Okay, and this is a special case of this, right? I can put a is equal to alpha, and then I can put b equals 0, c equals 0, d is equal to minus 1. I'll get that. Okay, just an example. But what is so peculiar about this example? It has 2 linear ODEs that are uncoupled. Okay, so I don't have the cross terms. So y1 does not have the y2 term, y2 does not have the y1 terms. In other words, this matrix A, B, C, D that I can build from here, this matrix is diagonal. Okay, so that's why I picked this example, because the matrix A, B, C, D, which it turns out will play a generally important role, we just call it A for a matrix. It will play a central role in what we're going to say. Okay, so it's diagonal in this case, and the diagonal elements are alpha and minus 1. Now, how does this behave? Now we know how this behaves, of course, because if you take this, then you can solve this. I mean, this is the most trivial ODE you can ever see. So I'm going to have y1 0. Let me call this initial point. So alpha is a little troubling. Let me call this initial point. Let me redraw this diagram. This diagram is not. It's too cluttered now. Let me redraw it. I don't need this layup on of business and so on. Let me take this as my initial point, and I'm going to call this. What do we call this? Let's call this P, Q, whatever, for want of a better letter, P exponential to the power alpha t. You can just solve this, and then this gives you y2 is Q exponential to the power of minus t. Okay, straightforward. Okay, most trivial thing. So what do these trajectories look like? Well, they depend on the value of alpha first, okay. But we'll keep this aside because we don't know what alpha is right now. It's just a constant. Depending on the value of alpha, different things can happen. But we look at y2. So the y2, no matter where you start, the y2 coordinate of the trajectory is going to decay away to 0 because of e to the power minus t. Okay, so if I start from here, this is the y2 coordinate q that I have here. This is eventually going to decay to 0. Okay. What happens to the y1 coordinate depends on the sign of alpha, naturally, right? If alpha is positive, then the y1 coordinate is going to increase. If the alpha is negative, then the y1 coordinate is going to decrease. And if the y1 coordinate, if the alpha is 0, then the y1 coordinate is going to be unchanged. So depending on the sign of alpha, you have different behaviors. Let's just sketch that out. So for example, if I start at this arbitrary point, let's say for alpha negative, when alpha less than 0, the y coordinate is going to reduce, the x coordinate is also going to reduce. So the trajectory is going to come like this towards the origin. This is when alpha negative. Okay. When alpha positive, this trajectory is going to go out like this. Okay, so this x1 is going to go out like this. Sorry, this is not the one. The x1 is going to go out like this because e to the power of positive times t is going to go out. Okay, but y2 is still going to reduce. So presumably, what is going to happen is the y2 is going to eventually go to 0, but the x1 is going to keep increasing, so it's going to go out like this and asymptotically going to become 0. Okay, so this happens when alpha is positive. This happens when alpha is negative, this happens when alpha is positive. Okay. Good. So what happens when alpha is 0? When alpha is 0, p, the y1 coordinate doesn't change, so it will just vertically go down like this. Okay. So let me draw a prettier picture of this. So y1, this is y2. For alpha positive, and again, there's another thing that is another subtlety, maybe I should mention that as well. For alpha negative, it's going to decay to the origin, but depending on the exact magnitude of alpha, if alpha is smaller, magnitude of alpha is less than -1, then this guy is going to decay slower than this guy. If magnitude of alpha is very large compared to 1, then this guy is going to decay faster than this guy, because e to the power of minus large number t is simply going to die out faster than e to the power of minus t. Okay? So you have to make that distinction. So for example, if alpha is very large, then the y1 coordinate decays faster. So if I start here, it's going to go like this. If I start here, it's going to go like this, and so on. It's going to go like this. So I can just draw these trajectories, right? So if if alpha is very large negative, the y1 coordinate will decay faster than the y2 coordinate, and eventually it's basically going to have the y1 coordinate is basically going to go to 0 very quickly, and then it's going to just go down vertically because the y2 is still reducing. If I had magnitude alpha less than 1, let's say if it's less than 1, then the opposite will happen. It will be like this. So this will come like this, like this, like this, and so on. So you can imagine what that will look like. Okay. So what have I drawn here? I've drawn trajectories starting at different initial points, all coming and meeting the origin. Okay, that's what I've drawn. Different trajectories. So depending on where exactly p and q are, you will have one of these trajectories that will follow and eventually come to the origin. Okay. Now if alpha is okay, maybe you can draw another special case as well. If I have alpha exactly equal to 1, it's all going to come like this. So this is alpha equals -1. Okay, it's going to decay to the origin like that. And why is that? Well, if you have alpha equals -1, then you have y1 is equal to p to the power of minus t, y2 equals q e to the power minus t. So y1 by y2 at any t is the same as p by q. So they lie on a line. So if this was the original point p comma q, then y1 by y2 will always lie on this line. Slope is the same. okay, line passing through the origin. So that's why it will come at a line. Okay, and if you have the third case, which is alpha positive, then what happens is the following. If I have alpha positive, then if I start exactly on the y axis, the vertical axis, the y2 axis, for now this I am drawing alpha positive. If I start exactly on the vertical axis, alpha is positive, then y1 is 0, exponential to whatever, doesn't matter, it's always 0. So you will always have y2 reducing with t. So this will come towards the origin, always come to the origin. So now I am doing the analog of what I did. Remember, for this guy I had a fixed point and I had this. Yeah, so this is a stable fixed point, we drew that before for the 1D case. Now for the 2D case, suddenly you are starting to see, just for this system, you are starting to see different possibilities. Okay, for the 1D case, okay, if I just change k plus minus, if I had a linear 1D system, k plus minus, this is either stable or it's unstable, we drew this, right? And so this is it, I mean, it's done, right? But now for the 2D case, already depending on the value of alpha, just 1, remember I fixed the other one at minus 1, just alpha, only one parameter I am changing and I am getting all these different possibilities. Okay, let's continue, let's finish this one, this is a little bit more interesting and then we will move to the others. If you look at this trajectory, the y2 again is clear, it's coming like this, but what happens when you don't have y2 but you only have y1? When you only have y1, it's going to go away because this is growing, alpha is positive. So anything else in between will basically come like this and go off. Okay. So now you have a saddle. This is a saddle point. This fixed point at the origin is a saddle point. Why is that? Because some trajectories come to it, other trajectories go away. For a 1D case, a linear system cannot have a saddle. Okay, when did a saddle come? If you remember from the 1D case, you only had a saddle if you did that f of y thing. If I don't know if people remember this, but if you do the f of y thing, saddle will come only when you have a non-linear thing that looks like this. A linear thing will just be like this or like this, no saddle. If you want to have a linear thing with a saddle, you need to have a V shape, and V shape will violate differentiability at the origin. Okay, so no saddle, 1D case. 2D case, you can have saddles like this. So you're starting to see more richer behavior again. Good. Okay, so that basically is what happens. Just with this single parameter, you can see all these things happening. Now I can do the same exercise if instead of this system, and I would encourage you to do this because the logic is exactly identical to what we have done, and if you have issues, please let me know and then we can go over it again. I would encourage you to do the same exercise if I had this. If I had this, what will happen? Now the situation is analogous, but okay, the values of alpha now, if alpha is less than 0, then you will have before I go there, for the negative case, let me just write it down. I didn't write it down. So for alpha less than 0, origin, which is the only fixed point here, is stable. Okay, for alpha less than 0. For alpha greater than 0, the origin, which is again the only fixed point, is a saddle point. Okay, I have to talk about the alpha equal to 0. What happens when alpha is equal to 0 here? When alpha is equal to 0, y1 does not change. It stays exactly where it started, right? So any trajectory you start from here will basically go down and hit the y2 axis. Y1 axis. Same with this. Same with this. Same with this and this and this. Okay, so all trajectories will come and hit the y-axis. Now this is a little bit strange. Okay, this is very strange because they will eventually get to one of these points. Okay, there are infinite of them on the y1 axis depending on where you start. Okay, they will eventually get to one of those infinite points on the y1 axis as t goes to infinity. So each of these points on the y1 axis acts like a fixed point. Okay, so this is a sort of pathological case, if you want to use that phrase. These are called non-isolated fixed points. We'll talk about them later, but it's just important to understand why they come. Okay, why do they turn up? They're non-isolated, which means isolated meaning this is an isolated fixed point because everything comes to this. There's no other fixed point in its vicinity. But here in the vicinity of the origin, which was the only fixed point for the linear system, you have infinite fixed points to the left and to the right, only along the y1 axis because alpha is 0. Okay, so this is what happens when alpha is 0. So we'll talk about non-isolated fixed points a little later on, but usually in most practical cases, you will either see alpha greater than 0 or alpha less than 0. Okay, good. So now let's go to the case where you have plus here. Okay, when you have plus here, the situation exactly changes. Okay, the same analysis goes through. I'll just write down what it looks like, and you can work it out later. Do the same, just draw the same type of pictures that I have drawn. Okay, and you will be able to figure this out. Okay, there's nothing fancy about this. So when alpha is positive now, this is going to grow. This is also going to grow. So this will be an unstable fixed point. The origin will be unstable. And when alpha is less than 0, this is anyway going to grow e to the power of t. This is going to go down, it's going to decay for alpha less than 0. So you will have a saddle in this case. Saddle fixed point. Okay, at the origin, of course. This is the only fixed point we have here. And at alpha equal to 0, again you have the same situation as before. You have non-isolated fixed points. No, okay, no, sorry. At alpha equal to 0, you don't have non-isolated fixed points. Okay, let me draw this. I should not just write stuff. So y1, y2. So if I just write this down, I'm going to get y1 is equal to p times exponential of alpha t, y2 is q times exponential of alpha t. Now if I have y1 equal to 0, this will be q. If I have if I have alpha equal to 0, this is plus t. If I have alpha equal to 0, then y1 is going to be unchanged, and y2 is basically going to grow with t. So if you start anywhere here, you're going to go away. Start anywhere here, you're going to go away. Okay. So this is different from the isolated fixed point case that we were talking about before. Okay, the isolated fixed point, everything was coming towards it. Now it seems to be going away from here. So if I take this point, everything seems to be going away. So you can think of these as being unstable in a loose sense. If you start close by, you're going away. By going away, start close by, you're going away, right? So loosely speaking, they're similar to the non-isolated fixed points that we saw before, but with their stability flipped. So that's something you want to keep in mind. Okay. Again, that happens only when alpha equals 0. This is alpha equals 0. Good. So what do we do next? Okay, so we know this system. Okay, this system and its sister system, the minus y21. We know what it looks like, and we know now we can see the 2D analog of the stable, unstable fixed points, and the 2D analog of a saddle fixed point, and these non-isolated fixed points. Okay, so you have the 2D analog of whatever we saw in the 1D case now turning up here. Okay. Okay, good. Let me do another example. Let me take this. Let me just call it P. Okay, let's take the general second order. Actually, let's make things easier for ourselves. We'll just take this system. Let's take this system. Okay. I'm going to convert this again, just like I do usually. So y1 is so dy1 by dt is equal to y2. dy2 by dt is equal to minus q0 y1. Okay. perfectly coupled. Unlike the previous case, it was perfectly decoupled. This is perfectly coupled. Okay, y1 does not have any y1 term on the right hand side. The y2 term does not have any y2 term on the right hand side. Okay. So what do we do here? We already know the solution to this. Of course, we have solved this. This is y is equal to some. Should I use a? Maybe I'll just use p. P sine of square root of q naught t. Okay. Plus, let's assume that this is the initial condition. Okay. The initial condition is. Let me do another thing. Let me first get rid of this and write it down here. So we've seen stable, unstable FPs, then we've seen the saddle FP, and then we've also seen this non-accelerated. There was no equivalent of this, but yeah, in the 1D case, but yeah. Okay. So let me pick a solution. So general solution, of course, for this is y is equal to a cos of square root of q naught t plus b sine square root of q naught t. I'll put the initial condition such that at y equals 0, at t equals 0, y is equal to a. Fine. So I'll just have y of t equals 0 is a, just for simplicity. Otherwise, I have to carry two terms around. I'll just carry one. So I'll just have y equals a cos square root of q naught times t, and dy by dt. So this is y1. Remember, if I convert it to this, that is y1, and dy by dt, which is y2, is basically a square root q naught with a minus sign, sine of square root of q naught times t. Okay, that's what y2 is. Okay, so if I take this system and match it back here. So what does it look like here? Let me draw a picture on the right hand side. I have y0, y1, and I have y2. This is at t equals 0, y1 okay, let me get, I've kept the unknown constant. I should put another initial condition to figure out what this constant is, but okay, whatever. So I'm going to start, let's say I'm going to start here with y2 equals 0. Okay. Or I'm going to start at some arbitrary point. Let me pick an arbitrary point. Okay, somewhere here. This arbitrary point is a, it's y1 naught, and this guy is at t equals 0. This is 0. Actually this is 0. Let me just do this. So t equals 0, y2 equals 0. So I have an arbitrary point here, a. I'm not paying so much attention to the boundary conditions, but okay. So this is where I start. And what does the trajectory look like? So this is a fixed point again. What does the trajectory here look like? This a is going to oscillate like a q0, square root of q0 times t, and the b is also going to oscillate but out of phase. So this trajectory will basically end up being like this. It will just go around and around and around and around this origin. Okay, the origin will be the center, it's not the focus of an ellipse type of thing, it's the center, and the trajectory is actually an ellipse, right? So this is an ellipse. The minor axis is a and the major axis is a square root of q naught. That's what this is, but it's an ellipse. Okay. Now this is an example of what is called a center. So now the origin is not a stable fixed point, it's not an unstable fixed point, because clearly trajectories that start from here are not approaching it as t goes to infinity. It's not an unstable fixed point, but it's actually a center. And the center is actually Lyapunov stable, because if I start close enough to this, I'll form another trajectory that goes around like this. Okay, so the center is Lyapunov stable. Okay, and it's not absolutely stable. okay, for the reason we've just discussed. So that's another thing that can happen. So we've seen all of this in that other system, but presumably you can also have centers. Okay. And if you have another term, now we conveniently took out the first derivative term here. If you had the other term that had plus p0 dy by dt, then you will have another term here. This will have a minus p0 y2 here. And if you leave this part out, this looks like the exponential part, the uncoupled 1D system that we derived. And so this term in this equation, in this 1D equation, is going to act like it's exponential minus t type of thing. So this is going to dampen, or this is, of course, if you solve this, this is the spring mass damper equation. You've probably seen this again. And this term is going to serve to dampen it. So it's going to make exponential minus something times t, something depending on q naught and p naught. And that exponential minus something times t will be on top of this ellipse. So it's basically going to start a trajectory here, and it's eventually going to come like this and reach the origin. That's a very different trajectory compared to the one we saw in the stable case. Stable case, it came and joined the origin. Okay, now it's going like this around the origin, it's spiraling into the origin. So this is called a spiral. Okay. And in problem in vibration, you always have P0 positive. So you will always see a stable, what is called a stable spiral. So now this point is not a center, but it's actually a spiral. This origin, because it's not a center, it's a spiral, and it's absolutely stable. It's not just Lyapunov stable, it's both Lyapunov and absolutely stable, because eventually trajectory will get there. Okay, and usually, like I said, in a vibration problem, P naught is always positive because the damping is always opposing the motion. It wants to prevent the inertia term from taking over. So P naught is usually always positive, but from a general differential equation point of view, P naught can also be negative. Okay, if P naught is negative, the opposite will happen, and you will have, if you start a trajectory here, it's going to go like this, and it's going to grow with time like this. So that is an unstable spiral. So you can have stable and unstable spirals. Stable / unstable. Okay, so you can have these additional things that didn't exist for the 1D case now suddenly show up just simply because you have two-dimensional phase space. Okay, so that's important. Now, we've seen just from these two examples, but you can get all these different interesting structures. Now, the next question will be, okay, how do I use this stuff if I gave you a matrix that generally had terms like this, all 4 entries A, B, C, D, and not just 2 entries removed for convenience, like I've done in the first example and the second. In that case, how do I analyze the problem? Okay, that's the next question you want to ask. And for that, the idea follows from here, and it actually builds on this idea of eigenvectors and eigenvalues that you probably learnt in the linear algebra. So let me put this system down here. Have dy1 by dt is ay1 plus by2, and dy2 by dt is cy1 plus dy2. Okay, and all this stuff, whether the excuse me, again, this is a linear system, so only one fixed point, only at the origin. We've discussed that multiple times. Please don't forget that. All of these behaviors are somehow encoded in this matrix. Okay, so all these all are encoded here. Okay, and if somebody, okay, you're walking on the street and somebody came and gave you a matrix, 2 by 2 matrix, and said, tell me about this matrix, the first thing you will do is diagonalize it, or try to diagonalize it and get its eigenvalues. And the second thing you will do is use those eigenvalues to calculate the eigenvectors. Okay, so presumably these behaviors are all encoded not just in the entries A, B, C, D, but in the eigenvalues and eigenvectors. Okay, eigenvectors and eigenvalues. So really all you have to do is look at the eigenvalues of this matrix and the eigenvectors of the matrix. Okay, and if you are going on the street another day and some other person comes and gives you a 2D matrix and 2 by 2 matrix, and they say, okay, what are the invariants of this matrix? There are only two. There is a trace, which I am going to call tau, which is A plus D, and there is a determinant delta, which is AD minus BC. Okay, so we have two invariants. So you can just characterize the matrix based on tau and delta. Okay. You won't say everything about the matrix because you also have the eigenvectors, but the eigenvalues you can say something about from tau and delta. What can you say? Well, if the eigenvalues are, if lambda 1 and lambda 2 are the eigenvalues, then because these are invariant, lambda 1 lambda 2 is delta and lambda 1 plus lambda 2 is tau. Okay, we have seen that before in the first part of this class. So since I know the origin and I know this matrix that multiplies this y1 y2 in the linear system, and presumably since one of these behaviors is which of these behaviors actually occurs is determined by the matrix. Okay, in one case we had a diagonal matrix and you had saddle blah blah whatever, and in the second case we had a completely off diagonal matrix, and then you had centers, spirals and whatnot, centers in that case, and then if you had added one more term you get a spiral and so on. So presumably it's all encoded in the eigenvectors, and if it's encoded in the eigenvectors, since the eigenvectors obey these two equations, they are basically encoded in tau and delta. Okay, so now we have to figure out what that encoding is, so that if somebody, again you walk on the street, somebody comes and gives you a matrix, you can say if the corresponding fixed point at the origin is stable or unstable. Now I want you to think about this for a minute. Okay, I want you to think carefully about this for a minute for the following reason. If you remember, again I am going back to this 1D system. If you did the linearization, you remember the linearization for 1D, this is eta. So when you do the linearization, the stability stuff was all encoded here. So presumably when you do linearization for the 2D case, which we will do later on once we figure out this 1D stuff, the information is now going to be contained in the matrix A. Okay, this matrix is now going to play a role analogous to this, or rather the eigenvalues and eigenvectors of that matrix is going to play a role analogous to this. Okay, we will see how that is in a minute. Good. So okay, you have a matrix and you want to find its eigenvalues. So then you just go to town, you have this, you have determinant of this equals 0, that is the eigenvalue problem. So you have a minus lambda, let me just write this down, it's like lambda square plus AD minus a plus d lambda minus BC equals 0. So lambda is two values, lambda 1 and 2 is a plus d plus or minus square root of a plus d the whole square minus 4 times AD minus BC by 2. Okay, this is the trace which we call tau. So presumably lambda 1 comma 2 is tau, which is here, plus or minus root of tau square minus 4 delta by 2. Okay, so those are the eigenvalues. Now let's go back to our original two examples, the diagonal one and the perfectly non-diagonal one, off diagonal one. So the diagonal one had a matrix that looked like this, alpha 0 0 minus 1. Okay, minus 1 plus 1 doesn't matter for now. And the perfectly off diagonal one had something that looked like this. It had minus some q naught and it had 0 like this. If you apply this to these two, here the trace for this trace is alpha minus 1 and determinant is minus alpha. For this guy, trace is 0 and the determinant is plus q naught. Okay, and these gave us all possible thingies going on over here, right? Except for the spirals, of course. I'll come to the spirals in a minute. But this is basically what we had. And if we take this and put it here, what do you get? So here, obviously, okay, this is trivial. The eigenvalues are lambda equals alpha and lambda equals minus 1. Lambda 1 equals alpha, lambda 2 equals minus 1 because it's already diagonal. So there's no reason to do this business. Those are the eigenvalues. What do you get here? Okay, here tau is 0, so this guy is gone. Q naught is positive, so delta is positive because it's plus q naught. So the square root becomes negative of something because it becomes imaginary, and so you will get lambda 1 comma 2 is plus or minus half, will go off with the 4 minus delta. So it will be plus or minus square root of q naught times I. So you have imaginary eigenvalues for this matrix. Okay, and remember what happened here. When you had imaginary, when you had this situation, you had a center. Okay, so remember this situation. You had a center, right? So now we can say very safely that whenever the eigenvalues, and of course eigenvalues will always be complex conjugate. If there is one imaginary, the other one will be negative of the same imaginary, right? They have to be. And or if the one is complex, the other one will be complex conjugate, okay, because they have to add up and give you a real trace, right? So the imaginary parts have to cancel out. And now we can say something about this question. So which of these occurs now depends on the eigenvalues. So in the first case, the two eigenvalues are both real. So when you have real eigenvalues, you either get stable or you get unstable, or you get saddles, or you get non-isolated fixed point. Okay, when you have real eigenvalues. When you have non-real or complex eigenvalues, if it's purely imaginary, you will get center. If it's purely imaginary, just like this is purely imaginary, so it was a center, we know the solution, we've seen that. If it's complex, which means it has a real part, then depending on the sign of the real part, lambda 1 and 2 will have the same sign of the real part, right, because they're complex conjugate of each other. So depending on the sign of any one of them, the real part of any one of them, if it's greater than 0, you will have a stable spiral. If it's less than 0, you have an unstable spiral. Okay. So now based on the eigenvalues, we've said something about, it's sort of sketchy, we're still guessing that this is the case. We'll give you a geometric picture of what exactly is going on so that now you understand what exactly this is. Okay, but so far so good. Okay. And depending again on the sign of alpha and the sign of the second fellow, depending on it's plus 1 or minus 1, you will get either stable, unstable, whatever the stuff we'd worked out before. Okay, so please make sure you correlate this with what we've done before. I only have a finite board, so I have to get rid of stuff periodically, but please go back and look at it. Okay, so let me give you a geometric picture of what this entire scheme is doing. Okay, geometric picture. And remember, we're still talking only about linear systems. I haven't said anything about nonlinear systems, and presumably the nonlinear systems are going to be much more complicated. But if you linearize them again, like we did, you can use the stuff we're saying now. Okay, and I wanted to think a little bit deeply about this idea, for the simple reason that all of this stuff is connected. Okay, finally you will see that the stuff we did for the 1D case is connected to the stuff we're going to do for the 2D case, the stuff we're doing already, and then the fact that you have a 1D phase space and the fact that you have a 2D phase space, you have oscillations possible now, we've just seen centers and so on. They're all connected. They're all basically part of one big picture, and I want you to appreciate that. Okay, so let's see, what are we doing? What is this procedure doing? So we've only looked at analogies, but we haven't said anything. So if I have a matrix, let's say I have this is again phase space y1, y2, and then I have the equation, the usual fellow, the dy1 by dt is ay1 plus by2, and then dy2 by dt is cy1 plus dy2, and then the matrix A is A, B, C, D. Running out of chalk. Okay, so if I have this situation like I had before, what do we do when we calculate an eigenvalue or an eigenvector, right? What are we trying to do? Well, if you take the matrix and if you diagonalize it, then you're basically looking for two directions, not necessarily orthogonal, they're just two linearly independent directions, along which the matrix basically becomes diagonal. So if I take this A and I diagonalize it, what am I doing? I'm basically looking for two linearly independent directions. Where the matrix basically becomes like this in that representation, right? That's what I'm doing when I diagonalize the matrix. So that means if I think about this as an operator, if I give this matrix two vectors, presumably if I give it two coordinates like this, vector made out of two coordinates, it's going to multiply them up and give me a third vector with two other coordinates, and that's exactly what this is doing. If I give it coordinates that are along the eigen directions or the eigenvector directions, then it will only scale them. Okay, so if the vectors are v1 and v2, it should be actually v1. Let me call the eigenvectors u bar and v bar. Okay, these are the eigenvectors. So v bar is v1, v2, u bar is u1, u2. Okay. Okay. If I give, let me write this down in a vector notation. If I diagonalize the matrix A, I give it v1 bar, then it's only going to scale it by lambda 1 corresponding to the eigenvector v bar. Let's call it v bar. V bar. Okay. Let's assume v bar. Okay, maybe u bar should correspond to lambda. Make it u. If I give it u bar, it's only going to scale that u bar by lambda. That's what an eigenvector is, right? And similarly, if I give it v bar, it's only going to scale that by lambda 2. So if I start, so if I can take these two directions, u and v, I'm going to plot them here. Let's say this is the u bar direction and this is the v bar direction. They don't have to be orthogonal, of course, unless the matrix is symmetric. And if I start a trajectory on u bar, so that is my initial point for this equation, for this differential equation. My initial starting point is on this vector in this direction. Then the right hand side, which basically determines the rate of change, as a result of this relationship, is going to make sure that I am always on u bar. Okay, let me repeat that again, just to make sure that everybody is on the same page. If I start my initial condition, so this will be my, let's say this is my initial condition, this is the original P, original Q that I had, right, for the initial condition for this linear problem. If the P and Q were such that they lay on this eigenvector direction of A, then simply because A times U is lambda 1 times U, A acting on P and Q will give me just a scaled version of P and Q, and the result will still continue to be on this line u bar. Similarly, if I start over here, if this was my P and Q, if this was Q and this was P, and if I started my trajectory here, because this is an eigenvector or eigendirection of the matrix A, I am going to stay on that eigendirection forever. And so, if I start here, I am going to be on this vector forever. Why is that? Because the right hand side matrix that is multiplying this will basically give me a resultant that is in the same direction. Okay. So, that is a very, very powerful construction. Okay. Why is that? Now, along these two directions, this general linear system has been decoupled. So, if I start on this, I am going to go either like this, or I am going to come towards the origin, depending again on the sign of the eigenvalue. Notice that if the eigenvalue is positive, then presumably I am going to go away. If the eigenvalue is negative, then presumably I am going to come towards the origin. Similarly, over here, but now sign of the second eigenvalue. If it is positive, I am going to go away. If it comes, I am going to come. Okay. So, along these two directions, so along u bar and v bar, the ODE has been decoupled. Okay. So, that is basically what you are doing when you are diagonalizing A. You are trying to find directions along which this linear generally coupled system becomes decoupled. Okay, and that is exact, well, that example we gave the start was completely decoupled at the start, and the matrix was diagonal. So, already you were in the eigendirections, y1 and y2 were the eigendirections. So, you were already doing this, you do not have to do anything additional. Okay. So, this means now that if the two eigenvalues, again keep that original analogy that we had, that example alpha minus 1 in mind, and you will see that what I am going to say makes sense. If the two eigenvalues are both positive, okay, lambda 1 and lambda 2 are both positive, then if I start here on this line, I am going to come towards the origin. If I start here, I am going to come towards the origin. And if I start somewhere in between, okay, no, I can split this up because this is two linearly independent vectors. I can break up any point here in terms of these two linearly independent vectors, and both of them will come towards the origin. So, the sum will come towards the origin and the trajectory is going to reach the origin. Okay. So, this will be a, sorry, this is negative. If this both are negative, okay, they will come towards the origin. So, this both are negative, then the origin becomes a stable fixed point. Okay. And you can imagine the exact opposite happening when lambda 1, lambda 2 are both positive. When they are both positive, if you start on this, it will go away. If you start over here, you are going to go away. If you start in the middle, you can decompose it into two components, linearly independent components, each of which is going away from the origin and eventually to infinity. So, the sum of those two will also go away. So, when lambda 1 and lambda 2 are both positive, then you have an unstable fixed point. Okay. Now, what happens when one is positive and one is negative? Well, that is easy enough, because if, let us say, if lambda 2 is negative, then if you start here you are going to come towards the origin, lambda 1 is positive, then you are going to go away. So, you will have the analog of what we had for the saddle case in that alpha minus 1 example. So, if you had, let us say this negative, this is going to come like this, going to go like this. So, any trajectory is going to come and go this, like this. Okay. Like this. So, if you have both of opposite signs, either lambda 1 greater than 0, lambda 2 less than 0, or lambda 1 less than 0, lambda 2 greater than 0, then you have a saddle. Okay. So, we know what to do now. Okay, we've got some rationale for saying when these things will occur based on the eigenvalues of the matrix. Good. Now, the next question will be, well, what if I can't diagonalize this matrix? What if the eigenvalues were complex? Right? We've clearly seen that if you have imaginary eigenvalues, then you're not going to find two directions in which this is going to happen. And so, if the lambda 1, lambda 2 were not real, they didn't belong to R, then you're presumably going to have a center or spiral, either stable or unstable. Okay, why is that? Well, because there is no axis along which the thing is either going to come towards the origin or go away from the origin, like we have here, because the axes are, the directions are complex, they are not real, right? And so, now you have a situation where the thing will just circle around it. If the real part of the complex conjugate values is negative, then it is going to be stable. If the real part is positive, then it is going to be unstable. Okay, and you can see that it will probably work out an example at some point to show you why that is so. So, you can see how that comes about. Okay. Okay, so this is all for a simple linear 2D system. You can already see the rich variety of behaviors that you can expect from here. And so, the stuff you can say depends basically on the eigenvalues of the matrix A. And the next step now will be to see if we can sort of visualize, if we can put all of this together in some form in a suitable diagram, so that we do not have to keep remembering this stuff. And it turns out there is, you can just look at the trace and the determinant, which I had written down here a minute ago. Just looking at the signs of the traces and the determinants, you can say which of these cases is going to come, and we will make a figure for that later on. And once we do that, we basically are armed with everything about the linear system. So, then we can take any nonlinear system, do a linearization procedure. Again, I haven't told you how to do that, I will say that in the next session. But if you do a linearization procedure, you will basically end up with the same system, but now A, B, C, D depend on where you are, which fixed point you are close to, and so on. And so, you can have different fixed points having different stability just by following this procedure at each fixed point. And you can now take it to the next level, and then you can say maybe there is the nonlinear equivalent of this with f and g on the right hand side, which I had written at the start. Maybe that has a parameter lambda. Okay. And now the fixed point stability depends on the lambda, and now things start becoming way more interesting. So, you can have a stable fixed point suddenly become unstable, you can have a center that was a spiral become a center, you can have all sorts of things going on. Okay. And so, this naturally the type of bifurcations you can expect in a 2D system is just now much more complex than the 1D system. Okay. And so, what we will do next is we will do the linearization. We will talk a little bit about this complex eigenvalues thing. We will derive a very simple diagram that relates the determinant and the trace to these characteristics of the stable point, again which is still at the origin, and then we will go to the nonlinear case and see how to approach that. Once we do that, I think we will be armed with enough knowledge of this entire subject. So, if somebody gives you a nonlinear equation, you should be able to linearize it and find the fixed points, first find the fixed points and then linearize about the fixed points, and then say if those fixed points are stable, unstable, and eventually use these ideas to say something about bifurcation of fixed points and so on, just like we did for the 1D case. I won't talk much about the bifurcations for this case because it's a little bit complicated, needs a little bit of time. But so we'll just stop at that point for this in the next session, and then we'll move on. We'll come back to the linear case and we'll talk about series solutions very briefly, and then we'll look at where they're useful in the context of PDEs and so on. And then that will sort of complete the loop from PDE to ODE to PDE. And then we'll go to, we'll have a very quick discussion of numerical methods. Okay, but we'll start with this and do linear stability analysis for nonlinear ODEs in the next session.